Okay, so good afternoon to all and welcome to lecture number 10. Yesterday we started chapter number 3, and in that we have studied uh, particularly the mathematical modeling of basic electrical components. So that we have studied in yesterday's lecture. Okay, today we'll study further. Okay, so just revise me. Now I'll not admit any more students. Okay. So yesterday, this was the example which we have taken. So just I'm taking recap of that example. Means you can design any electrical system, okay, or electronic system. So yesterday we talked about this is RC low pass filter, and if you'd like to, okay, so this RC low pass filter, we have found the transfer function of this RC low pass filter, which is equal to 1 upon 1 plus RCS, and from this transfer function, you will come to know that there is one pole which is located at minus 1 by RC. Now you can easily, okay, design the RC low pass filter uh, such that, okay, its pole will be at -3 or something like that. So if you equate this one equal to -3, and if you assume value of R equal to 1 mega ohm, then you can easily calculate the value of C, right? So if this value of R is equal to 1 mega ohm and C is equal to 333 picofarad, then this pole will be located at -3. So you can design as per your requirement. Like if you want the pole to be at the location of -5, so you have to put this one as a -5 by assuming one parameter or one component. You can find the other component. So either you can assume capacitor, standard value of capacitor, find out the value of resistance, or you can assume standard value of resistance, you can find out the value of required capacitor, so that it will locate or it will place the pole at desired position and so on. So that is what we have studied in last lecture or yesterday lecture. Now in today's lecture, we'll talk about the mechanical system, how to find, okay, how to do the mathematical modeling of mechanical system. So in electrical system, we have studied that for doing the mathematical modeling of that electrical component or electronic component, okay, we are using the basic rules of that field. So in electronic or electrical, okay, field, the basic rules are Ohm's law or Kirchhoff's current law or Kirchhoff's voltage law. So these kind of laws are there, so which we have used for doing the modeling of the electronic component, like as a resistance, inductor, and capacitor. Similarly, in the mechanical system, you see, yesterday we have seen that most of the electronic circuits are made up of resistance, capacitor, inductor, diode, transistor, and so on, right? Even if there are IC, inside the IC, there are resistances or capacitors or inductor or transistors and diodes and so on. So this basically resistance, capacitor, and inductor are the basic elements, okay, with which you can design any kind of circuits and so on, okay. Similarly, in case of mechanical system, okay, now we'll see what is by mechanical system, what are the basic element with which we can design the mechanical systems and so on. And then see why we are studying this mechanical system in electronics engineering, because you can design the this one mechanical systems in terms of electronic. You know that the cost of mechanical component is very high, okay, whereas cost of resistance electronic component like as a resistor, capacitor, or inductor is very less. Like resistance will cost around 1 rupees, or capacitor 2 rupees, inductor 3 rupees, or something like that, okay. So cost of electronic component is very cheap, okay, or very less, whereas mechanical components are very high. Cost of mechanical components is very high. So can we design those mechanical systems in terms of electronic systems? Is there any analogy or like that? So that we are going to study. But before that one, we are studying individually electronic systems mathematical modeling of electronic systems, then mathematical modeling of mechanical system. Then we'll find out the relation between this analogous relation between electronics and mechanical system. And then after that, we can think, can we design mechanical systems in terms of electronic component and so on. So that is okay. That's why we are studying here this mechanical system. Now you know that in mechanical system there are three types of basically systems. One is translational mechanical system, where your motion is a linear motion, right? Means, like for example, if this object is moving in this linear like this, so it will have the linear motion. But like for example, if object is rotating around its axis, then it will have the rotational motion. Whereas okay, if object is just moving in this direction, okay, then it will be having the linear motion. And that linear motion is that kind of systems are called as the translational mechanical systems. But the objects, okay, or the system which is rotating around its own axis, then that system, mechanical system, is called as the rotational mechanical system. Like for example, there may be a combination of rotational and mechanical, okay, this one rotational and translational system. Like for example, if you take the example of car, okay, so car is moving, okay, in a straight line or in a curved path or something like that. But okay, for that car there are wheels, four wheels are there, which have the rotational system, and the overall car is having basically a translational mechanical system and so on. So like that way, there may be a combination. And also another thing is that there may be a linkages, like as a gear system is there, which transfers the basically motion and so on. So that is called as the mechanical linkages. But from electronic side, okay, we'll concentrate only on this, okay, for understanding purpose, because our subject is a fundamental of or basic subject of this one control system. So we'll limit our study up to this rotational translational mechanical system and rotational mechanical system. Now see that first we'll study in this lecture, we'll study about the translational mechanical system. So translational mechanical system, as I said, that its motion is in linear. Okay, it has a linear motion basically, or object moves either in a straight path or in a curved path or something like that. Object moves in the straight path or curved path. Now this is the example of your this one translation mechanical system. Suppose for example, if we apply a force, so this is the mass element, and this is the spring element, and this is the dashpot or something like that, and it is one end of this spring element, and dashpot is connected to the reference. Now if I apply a force on this one, what will happen? This mass will basically push to this this one dashpot element, and then spring element, and then there will be linear motion or linear displacement will be there. So this linear displacement is basically given by x. So x gives the linear displacement, and force applied on this one is the this one in the direction, so it will have the linear displacement. As I told you, okay, let me clear first one thing is that in case of mechanical system, I said that there are two systems. One is translational mechanical motion is in linear, or I that
Sir, your mic is off for A division.
Okay, now it is on.
Yes.
Okay, fine. Just I'm sharing my screen again. Okay, I hope that now screen is visible to A division as well as B division, right? Is this fine?
Yes, sir.
Fine. Okay, thank you. Thank you very much. Okay, I was talking about this basic system. Okay, in mechanical system, there are two types of system. One is translational mechanical system, where your motion is in linear motion is there, or object moves in a straight line or in a curved path. Whereas in rotational mechanical system, okay, object moves or rotates in around its own axis. So this is a rotational mechanical system, whereas this is a translational mechanical system. So if you apply force on this one, so there will be linear displacement, which is given by x. Okay, and as I said that then, okay, in electrical system or electronic system, there are three basic elements with which we can design any kind of circuit. One is resistance, another one is inductor, third one is capacitor. Whereas in case of mechanical, translational or rotational mechanical system, there are three basic elements. One is called as the mass element, another one is called as the dashpot element, and third one is called as the spring element. So you might have seen that. Okay, for just, okay, take the example of train. So this is just like as a bogie, and in between two bogies there, okay, you might have seen that the spring is connected between two bogies and so on. Or you might have seen that shock absorber is there for two-wheelers, or even for, okay, for even every vehicle there shock absorber is there, or brake system is also there. So that is nothing but basically dashpot kind of thing, or it is also called as the damper or dashpot. Okay, and this is a spring element, and this one is the mass element. So what I mean to say that, okay, like electronic system, there are three, in electronic system there are three basic elements. One is resistance, inductor, capacitor. Whereas in mechanical system, mechanical systems can be designed with the three basic element. One is mass element, another one is the spring element, and third one is the dashpot or damper element. So this is available in the rotational as well as translational mechanical system. So what we will do, like yesterday we have studied how to find out the mathematical modeling of individual resistance, then individual capacitor, then individual inductor, and after that we connected the resistance and resistance and capacitor, and then we found out the transfer function of that one. And then after that, okay, we can basically design any kind of circuit, and then we can find out the transfer function by using basically basic laws in that field. So you know that basic laws which are used in electronic systems or electrical systems are Ohm's law, or Kirchhoff's voltage law, or Kirchhoff's current law, and so on. Whereas which are the basic laws which are used in mechanical system? So you know the well-known laws which are available for mechanical systems is nothing but the Newton's law. Okay, so there are three Newton's laws, and which we can use for doing the, okay, obtaining the mathematical model of physical system and so on. So what we'll do, we'll obtain individual transfer function of this spring element, we'll obtain individual transfer function of this dashpot element, and then we'll obtain the individual transfer function of this mass element, and then overall transfer function of this system or any kind of system we can obtain the transfer function and so on. So translational mechanical system, okay, so as I said that, okay, this one, translational mechanical system, you have the spring element, you have the mass element, or you have this dashpot element. Okay, so when you, okay, see, there are two ends of this spring element. One is this V2 end, another one is V1 end, and if you apply force on this one, so how much will be displacement of this spring element, having constant k as a constant for this spring element. Similarly, for example, there is a V2 one end of this dashpot, and V1 is another end of this dashpot, and you know that, okay, so just assume that shock absorber, okay, it will, okay, when you apply a force or like this, so it will go down, and then again when you release the force it will come up. So this kind of arrangement which is used for shock absorber and so on. Now there will be displacement, linear displacement. So how much linear displacement will be there for this one? So see, this is the this dashpot element, or like as a shock absorber. So it is having two terminals. One is V2 terminal and another one is V1 terminal. And if you apply force on this one, what will be the displacement that we have to find? Similarly, okay, so this is basically mass element, okay, mass element, and then this is a dashpot element. So V2 and V1 is the this one, two ends of this one, and okay, and this is the mass element again for this one. V2 and V1 is there. Now we'll find out the transfer function, or basically mathematical modeling of every or individual this one spring element or mass element or dashpot element, and then we'll combine it. So in translational, spring is a mechanical element. So this translational mechanical system, this spring is a mechanical element that can be deformed by an external force such that the deformation is directly proportional to the applied force on it. So this kind of spring you might have seen in two-wheelers also, or even in train also, in four-wheelers also, and so on. So when you apply force on this end, okay, so spring will get compressed, and okay, there will be displacement, linear displacement of this one. And when you release the force, okay, spring will come back to its original position. So how much displacement is there with, okay, the applied force that we can calculate, okay, for this translational spring. So this is the actual translational spring, and the circuit symbols are like this. For spring, symbol is like this, where it has two end. One is end is this one, V2, and another one is V1. And if you apply force on any end, then how much, okay, if you apply force, okay, outward side, definitely this spring will get stretched. If you apply a force to the inward side, then spring will get compressed or like that. Okay, but when you release that force, it will come back to its original position and so on. Now, so when you apply, like for example, if there are two ends are open, and if you are applying the force, or suppose for example, if there is one end is connected to the some reference, or like for example, there is a wall, and for this, okay, to this wall, one end of this spring is connected, and other end, see that you are pulling just that spring. So definitely this end will be at this location, but this end will have the displacement. So here, if you are considering this as the x2 and this end as a x1, so x2 will not change, its location will not change because it is fixed at the wall side or reference side. But when you apply force on this end, x1 will be there. So see that if F is applied force, okay, if F is applied force, then x1 is the deformation if x2 is equal to 0, or x1 minus x2 is the deformation. But now x2 is 0, so what will the total deformation? That will be equal to x1. So this one, this equation of the motion for the spring is given by F is equal to, or force is directly proportional to the displacement. In case of spring, force is directly proportional to the displacement, and proportionality constant is nothing but the spring constant. So this K is nothing but the spring stiffness, or which is expressed in Newton per meter. And so this force equation for the spring means force is directly proportional to displacement. So how much is the displacement? x1 minus x2. But now x2 here, in this case, x2 is 0. So if you put x2 is equal to 0, then what will be the force? Okay, so this force will be equal to k into x1. So that will be the equation. But if one other end is not fixed, like for example, x2 is not fixed, then this equation will be like x1 minus x2, right? So I hope that you have understood how to find out the mathematical equation of this spring. So mathematical equation, so spring is like, okay, like this, it has two ends, x1 and x2. And if x2 is fixed here, in this case, and if you are applying the force at x1, so definitely the spring will get if spring, okay, force is at outward side, then spring will get stretched, right? and then there will be displacement at x1 end. But if you apply the force on, in inward side at x1, then spring will get compressed, and then x1 will be in other direction, like in this direction. But if you are stretching, it will be in this direction. So this, how much will be the force offered by, reactive force offered by this spring? So that is given by force is directly proportional to the displacement, and this directly proportional. So proportionality constant here is k. K is nothing but the stiffness constant of the spring. So we can write the equation of spring as F is equal to k into x1 minus x2, right? So F is equal to k into x1 minus x2. Now here, if one end of this spring is at reference, so x2 will be 0. So in this case, so this displacement will be equal to F is equal to k into x1, or like that. And this k is nothing but the stiffness or spring expressed, stiffness or stiffness of spring, and which is expressed in Newton per meter, right? Now, suppose for example, there are more than one springs are there in that system. You might have seen that in railway also there are two springs connected and so on. So sometimes springs may be connected in series, or some spring may be connected in parallel. So how much will be the displacement? Like for example, if two parallel connected springs are there, and if you apply, means parallel means both the end of this, one end of this one is connected with another, one end of this K2, and then another end of K1 is connected to another end of K1. And then if you basically apply a force, so how much will be the overall displacement if two springs are connected in parallel? Similarly, question is that if two springs are connected in series, what will be the total overall spring stiffness constant, and then what will the overall displacement, and when you apply the force like this, right? So we'll see how this, like for example, there are two springs with the spring constant K1. So this constant, this spring is having constant K1, and this spring is having constant K2. And we have to obtain the equivalent, spring constant equivalent, when two springs are connected in parallel. Also, when two springs are connected in this one, series, and so on, right? So we'll study that one. Now see that when two springs are connected in parallel, what will happen? The displacement of K1 and K2 will be same. Now when you are stretching both the end, like for example here, one end of K1 is connected to reference, and another end of also one end of K2 is connected to reference, whereas another end of K1 and K2 is connected together, and the force is applied to this one. So definitely when you are applying force like this, so K1 and K2 will get stretched, but the displacement will be same now for K1 and K2 when it is connected in parallel. So the two springs having same displacement, therefore, so K1 into X will be the displacement of this spring, and K2 into X will be the displacement, force of this spring K2, and which is equal to F. So F is equal to K1 X plus K2 X. So X is the overall displacement of these two springs. Now, if you take the X common, then this K1 plus K2 into X, which is equal to F. So what is basically this K equivalent is, this is nothing but the K equivalent. So when two springs are connected in parallel, the equivalent stiffness of that spring will be just summation of the stiffness of K1 and K2. Similarly, if there are n springs connected in parallel, so we can generalize the equation that equivalent stiffness of n springs connected in parallel will be equal to K equivalent equal to K1 plus K2 plus up to Kn. Means when two or more springs are connected in parallel, then in that case, basically, the equivalent stiffness of the spring will be just summation of the individual stiffness of spring. So K1 is the stiffness of spring first spring, K2 is the stiffness of second spring, and Kn is the stiffness of nth spring, and so on. So I hope that you have understood. Means when two or more springs are connected in parallel, then equivalent K equivalent will be just summation of this one. So it is just like as resistance is connected in parallel series, right? That or capacitor connected in parallel, or like that. Similarly, when two springs are connected in series, like series means, see one spring of this, one end of this spring K1 is connected to the reference, another end of K1 is connected to the one end of K2, and other end of K2 where you have applied the force. Now there is a displacement x1 of this K1 and there is a displacement of x2 of K2. Now when you apply force on this one K2 end, so there will be different displacement on K2 as well as K1. So overall there will be basically displacement. So the two forces on two springs are same. F, okay, so two forces on two springs are same. So F, however, displacements are different. Okay, forces are same but displacement are different. So K1 into X1 equal to K2 into X2, which is equal to F. So F is nothing but K1 into X2, okay, K2 into X2, and F is also equal to K1 into X1. So K1 is the stiffness of spring 1 and X1 is the displacement of spring 1, K2 is the stiffness of spring 2, and X2 is the displacement of spring 2. So when force is applied, this force is equal to this displacement, okay, as well as this displacement. So K1 into X1 equal to K2 into X2 is equal to F. So X1 is equal to, so from this you can find out the displacement. X1 is equal to F by K1, okay, and X2 is equal to F by K2. Now if value of K1 is different, then definitely displacement will be different for K1. So like for example, stiffness is less, so there will be more displacement for this one. And if stiffness of this K2 is okay, is high, then there will be less displacement. So overall, see, force is same, but displacement will be different, and it depends upon the stiffness of individual spring. So since we have applied the same force, so this force is equal to K1 into X1, and which is equal to K2 into X2. So you have got two displacement, different displacement, and overall displacement will be equal to what? This displacement plus this displacement. So since the displacement X is equal to X1 plus X2, and we have basically to F is equal to K into K equivalent into X, we know that force is directly proportional to the displacement, and this proportionality constant is nothing but the K equivalent. Now see that X is equal to X plus X1 plus X2, and you know the value of X1, which is equal to F by K1, and X2 is nothing but F by K2. So this is equal to F by K equivalent. So what will be the basically K equivalent value? 1 by K equivalent equal to 1 by K1 plus 1 by K2. Similarly, if you connect n spring in series, what will be the equation? So F by K equivalent will be equal to 1 of F by K1 plus F by K2 up to F by Kn. Right, that like that. So when two springs are connected in series, equivalent stiffness of those springs will be equal to 1 upon K equivalent equal to 1 by K1 plus 1 by K2 plus 1 by Kn, and so on, like that way. Okay, I hope that you have understood the equivalent stiffness equivalent of the springs when they are connected in series and when they are connected in parallel, right? So see that F by K equivalent is equal to by K1, and so if n springs are connected in series, then K equivalent will be equal to K1 K2 up to Kn divided by K1 plus K2 up to Kn. So this is the equivalent stiffness of the spring, right? Now we can obtain basically, sometime it may happen that we may have we may have two springs connected in parallel, and then these two parallel combination is connected in series. So it will have one displacement F X1, and this will be having X2. Okay, if somebody asks you that, can you find out overall K equivalent for this one? So how you are going to find? So basically the K equivalent for this parallel combination will be K1 plus K2, and then this one will be equal to 1 upon K1 plus K2 plus 1 upon K3. So if you solve that one, you'll get the total overall K equivalent. I hope that you have understood this one. So what is the K equivalent of this parallel combination? K1 plus K2. Also this will act as a K1 plus K2, and this is connected in series with K3. So overall this one, K equivalent will be equal to 1 by K equivalent equal to 1 upon K1 plus K2 plus 1 upon K3. So this will be the equivalent stiffness of this example. Similarly, what will be the this one? How you are going to do? So this K2 and K1 are connected in series. So okay, K2 and K3 are connected in series. So you have to obtain the K equivalent of that one. And then after that, K1 will be connected in parallel with this one. So you have to obtain the overall stiffness of this one. So I hope that you can do it once you have understood this one. translational spring system. Now another element of translational mass element, so that see, like for example, if this is the mass element and if I push this one, so definitely when I apply a force on this mass element, it will operate opposite force. So this opposite force offered by this mass element is directly proportional to the acceleration. Okay, so see that opposite force offered by this spring element was directly proportional to the displacement. Now this one for mass element, when we apply a force will offer a reaction. Is directly I think now we are at the end only. Just 1 minute. So I'm connected to B division as well as now I'm connected to A division. A lot of problems are there here. So for A division now screen is visible.
Yes, sir.
Okay, now for B division also I'm sharing it again. I don't know, automatically it is disconnecting. Okay, I hope that now for both division it is visible, right?
Yes, sir.
Okay, fine.
Yes, sir.
That's good. That's good. Okay, so I was talking about this mass element. Okay, so this mass element is an integral part of any mechanical system. So this is also called as the inertia element. And when you apply force on this one mass element, basically this will offer a reactive force also, and then there will be displacement. So this displacement is given by the Newton's law. So this force is directly proportional to the acceleration. So okay, proportionality constant is m, so that's why we have replaced with this equal to and m. And then acceleration is nothing but, see that x is the displacement, what is the velocity? That is derivative of the displacement is nothing but the velocity. So dx by dt is nothing but the velocity. And what is the acceleration? Again, derivative of velocity is nothing but the acceleration. So if you take the double derivative of displacement, you'll get the acceleration. So that's why I have given this x is nothing but the displacement, and then x double dot is nothing but the acceleration. So mathematical model of this mass element is f is equal to m into x double dot. And whereas mathematical model of spring element is that okay, displacement in the spring is given by f is equal to k into x. So that is the mathematical model of spring, which is given by Newton's law. Similarly, here mathematical model of mass element is f is equal to m into x double dot. That is nothing but it is directly proportional to acceleration. Similarly, the dashpot, which is the last element in the mechanical system, translation mechanical system. So you might have seen that this is just look like as a your shock absorber or even brake system and something like that. So if you apply a force, so definitely this okay shaft will go inside, and then this part will be at one side. Okay, one side will be remain. So sometimes it is filled with a gas or air. So it is okay, or sometimes it is filled with the liquid, like for example oil may be there and so on. So which will offer the resistance, right? So when you apply force on this one, so definitely there will be displacement of this shaft, and this displacement is given by the Newton's law, which is directly proportional to the velocity. So velocity is nothing but a derivative of displacement. So d, if x is the displacement, so its mathematical equation will be equal to what? So dashpot f is equal to if we are considering this as a b coefficient, so b into dx by dt. So when the viscosity or a drag is not negligible in the system, we often model them with the damping force. So this is called as the damper or dashpot, something like that. So all the material exhibit the property of damping to some extent. Like damping is basically it is offering resistance. So if damping is in the system is not enough, then extra element, that is dashpot, are added to increase the damping, right? Now see you might have seen that such kind of things are there in vehicle suspension, okay? Or this is nothing but the shock absorber now. Also you might have seen that when you're opening the door, so automatic door closing system is also having the door stoppers are also example of your dashpot, or bridge suspension is also having the dashpot, or if flyover suspension is also having the dashpot system, and so on. So in every mechanical system you will find this component which is called as the damper or dashpot, and so on. And symbol of this one is like this. So one end, like this is the shaft, and this is filled with either gas or air, or it is also filled with liquid, or this one. So when you apply a force on this one, so it will basically there will be displacement, and this displacement is directly proportional to the derivative. So that's why, and this proportionality constant, if it is c coefficient of this one dashpot is c, then f is equal to c into derivative of x, or it is nothing but the velocity. X dot is nothing but the velocity. If both the ends are open in this case, so it will be equal to f is equal to c into x1 dot minus x2 dot. So velocity at x1 and velocity at x2 and so on. So this is the mathematical equation of damper. I hope you have understood this one. So just to summarize, see that when you apply force on a spring, so the displacement is directly proportional to displacement of spring is directly proportional to the displacement, right? X. When you apply force on dashpot, displacement is directly proportional to the velocity, so dx by dt. When you apply force on mass element, its displacement is directly proportional to the acceleration. So F is equal to m into dx d2x by dt square, and so on. So that is what we have planned for today's lecture. So what we have studied is mathematical modeling of three basic elements which are used in mechanical system. So we have studied there are two types of mechanical system. One is translational mechanical system, and another one is rotational mechanical system. So in today's lecture, we have studied translational mechanical system and the components which are used for that one and its mathematical modeling. So in tomorrow's lecture, we'll take further study of this mechanical system. Okay, so thank you very much. We'll stop here. If you have any doubt, you can ask the question. Okay, any question, please?